Hello everyone, today we're back again on CodeForces, this time Division 3 round. Thank you so much for everything, for the whole support. This is round 888, cool number. So there are a lot of people. This will be recording, will be uploaded on YouTube as soon as the round finishes, so there won't be any conflicts, of course. And so check out the other videos again on my channel for other rounds or some other explanations. There will be soon video for my setup. I use this particular CPH Judge extension and program mostly in C++. So I will explain everything of every component of my setup. There will be explanations at the end of the video as always, so I will go over the problems. And yeah, that's pretty much it. Let's just try to solve them. Okay, so there are a total of n passengers. The escalator has total of n steps, each step from 1 to m. I step has a height of I times k. Okay, what's height is h centimeters? Two people with a height a and b can have a conversation on the escalator if they're standing on different steps and the height difference between them is equal to the height difference between the steps. For example, if two people have this height, and m is 10, k is 5, k is, what is this, 5, okay, 10 steps. Then take step number 7 and 5, the height difference between is equal, okay, given an array h of size n. So there's n people, and height of each person is how many people can have a conversation with on the escalator individually. What is interesting in how many people he can have a conversation with on the escalator individually. So the height difference has to be smaller than, so what is the Vlad's height difference? The height is h. So he says k here, m, and if Vlad can have a conversation with a person with height 5, okay, so Vlad has height 11, but where do they have to stand? 5, okay. The absolute difference between his height and the person's height has to be smaller or equal than the where the height, if they're standing on different steps and the height difference between them is equal to the height difference, okay, so it's equal, so it has to be divisible. So okay, so there's a couple of numbers here, n, m, k, and h. So here there's some person x with height x. Height is up to 10 to the 6. So now here is we're going to count the answer. The answer will be if the absolute difference between this, so this is like the difference in height, if the difference in height is divisible by k, has to be divisible by k, and the difference in height is at most m times k, because it can be at most m times k things, or maybe like smaller than m times k or something. Has to be divisible by k, because if this here, oh, it has I times k, so I times k. This is not has okay, so this is not equal that, but actually I times k is 1 times something, 2 times, but that sum here is a quadratic equation, thus meaning that I don't understand how this can be problem A. The steps are wait, m goes up to 50. Can we brute force for like j times k? This is the sum if sum is equal to the difference insert plus plus and break. From 1 to m, the height from 1 to m, the height is I times k, then the sum here is, yeah, but it can start from anywhere, so wait, there's n times 50 times isn't that a lot? No, that's not a lot. So like this is like from the where do we start? Then when we okay, so we can start from anywhere. You start from anywhere until this is the condition. The sum is equal to the height difference. Maybe we can't, no, it's just indexing here. Maybe we can't start from, no, it's fine, this is fine. No, it's just like where am I plus where, my step has this height. I can step to anywhere I want, right? but because they are all there's some math behind this, but I just don't have time to prove it. This is a brute force approach here. So I just sum up until this. If the sum is equal to some difference, let me this is definitely not 0, 0, 2, and 4. Wait, height of 2, the first case explained in the sum is 4. Why sum is sum is 9. One times k 3, and then 2 times 3 6. So how many steps are here? To the difference in steps I'm not sure. Like no. Wait. The difference in steps. This has to be divisible and plus what? It has to be divisible by k, right? Yeah, you can form anything here. Like I don't need this. I think the formulation is, and I need to prove this, but the difference has to be divisible by k, and k times m k times m times, I'll just long use here, k times m minus 1 divided by 2 has to be bigger or equal than the difference. Why this doesn't work? The height here, it has to be divisible this, but you can create any other. Yeah, but the subset, yeah, no, you can't, but because this is not a subset, this is no, you can't do that. So j times j plus s difference the sum here is 9. 9 is what? J and S. 2. The j is 2, so from 1 to times k. Okay. And then, okay, so the difference in steps their height difference is 9. This is difference. How is this? Oh, this is the I step has a height of I. Oh, this is. I thought I was solving something else. Wow, this is no. It's essentially. It's essentially this. Yeah. Okay, so yeah, why not just okay, k times what? Just do long here. Difference has to be divisible by k, and can they be equal? Maybe if difference is equal to like h. No, it's like, yeah, if like the difference is equal to 0, maybe we want to like continue. Okay, whatever. Stupid problem. This is a very bad problem, but whatever. Can't believe it. We have an array. Can apply the following operation: swap two elements. They're both even or both odd. Determine whether it's possible to sort the array in decreasing order, in non-decreasing order by performing. Both even or both odd. So what about you could sort? So you could sort first the even numbers, right? Because they can only be swapped. So you can just sort the even numbers. And then you could sort the odd numbers, and that would be like. So if this is an even number, even pushback 0, AI. So I will make like a pair int. They're all integers, right? Yeah, they're all integers. So I will just push it I with like where that thing is. And then I could sort even, and I could sort odd. And then for each, again, even number, or for each, so like this, I could do this. So I put them back into their places, and I ask is sorted. Even odd numbers. Odd numbers are right. There's something wrong here. So for every even number, I sort two and five. Yeah, of course. So 2 and 5, of course, I need to bring them back into the I need two arrays. I need two other arrays that will remember the indices of these numbers. So like this, like index here, and then I could have like even ID pushback I, and even ID an odd ID pushback I. Yeah, and then for each of the, so I will go like this, for each of the even numbers, even at I dot first is my number. So there's going to be like A at even ID of so this is sorted. The even ID of I, A at that ID is going to be equal to this. And this is the same for odd. I will explain at the end. So this looks good. Tiles come back. Remember the Hessian series of n tiles in number k, left from right. The I tile has color CI. If you stand on the first tile, start jumping a number of tiles on the right, you can get a path of length p, the length of the path, number of tiles you stood on. Once to see if it's possible to get the length of path such that it ends with a tile on index I, and p is divisible by k. The path is divided into blocks of length exactly k each. Okay. Tiles in each block have the same color. The colors in adjacent blocks are not necessarily. So the path is divided into blocks of length k. The color, what consisting of 2 blocks. So yeah, you jump first here, then here, then you jump here, then here, then here. Okay. Let me just see. Of course. Okay, so the path that the blocks need to be exactly k each, and p is divisible by k, so p will be divisible by k. If the blocks are k exactly each, then it ends on the tile index n. So the colors in adjacent blocks are not necessarily different. Well, can't you like always construct this? Not necessarily different. P is divisible by k. Yeah, it depends like on k, right? So k. So the first color, it's already given. Then you have to have k from the first color. So I'm gonna take the first k from the first color, and then the trick is like from the last color, can we get k from the last color? Because like it just doesn't quite matter. I'll save them in some array. So the first pointer here, so from the front there's some pointer, and from the back there's some pointer. And then int c0 and int c1. So this is like c front, the color on the front, how many count there is, and the color on the back, how many count. If a of I is equal to a of 0, color on the front plus, if color on the front is k, then front is equal to I. This is the last time this color we can achieve. This is the shortest time. Then I go from the back and I do the same thing, and then I can say if front is smaller, this is n-1. If front is smaller than back, then it's yes. Otherwise it's no. maybe equal. Can they be equal? No. You have to see the first color, and then you have to P is divisible by K, it ends on the index N. So let's say here, this third example is this guy, then there's 3 colors, and there's no, because yeah, so CF has to equal to K, and CB has to equal to K. Okay, now here, why is this no here? 2 on the front and 2 on the back. Well, this is no, but wait, can you tiles in each block have the same color? The colors in adjacent blocks are not necessarily. Each of length K. Can you jump on the same block twice? Here, why is this? Yes. Wait, from here you jump to here, and then you jump again. Only once. So yeah, so like if color, if front, if A of 0 equals A of n minus 1, and CF is equal to K, or CB is equal to K, then you can change one of these, and then it will be yes in this case. Okay, let's go D. Your friends with n elements your friends have an array with n elements. You're not friends with n elements. Calculate its prefix. Calculated its array of prefix sums and passed to you. The accidentally losing one element during the transfer. Your test is to find out the given array. If the given array can match permutation. A permutation of n elements. Yeah, so the prefix sums. So the prefix sums yeah, so because one element is missing, we can the difference between these two elements can be an element of the permutation, or it can be like a sum of two elements inside the permutation. But when we have like all the differences between these two, there will be either one difference that is bigger than elements in the permutation, or one difference that corresponds, like fulfills some other difference as well. And then what you can do is, so you need just to say like if it's yes or no. Okay, so I guess, let me just see the standings. I guess you could just so what I will have is like, I'll have some like difference thing here. Oh, this is n minus 1. The difference thing here, we go from 1 to n minus 1. And here is place 2, of course, and then d push back a of I minus a of I minus 1. So this is the difference. Then we want to sort the difference. After sorting the difference, there will be like two same differences, or there will be a difference which is bigger than n. Okay, so I'm going to use a set here, or not a set, like a frequency map. To avoid so the iterator here is like, if the iterator dot first is bigger than n, it means that it's like this element is a sum. This element is a sum of two elements. Yes, and then if it's not this, I will say that, so then there's this thing, if the frequency is 1, if the frequency is 1, then we kind of wanna the frequency is bigger than 1. This element is also a sum of two elements. Yeah, so IT first is true, so this is visited. If it's a sum of two elements, what do we say that is a sum of two elements? Well, there's only one element missing, which means that like this can happen only like once. So failed plus plus, I will add just precautionary check here. So if it's like multiple times failed, then is bigger than 1, then there's no way to do this. Okay, so let's say that this has failed once, So the visited here has to be like, okay, so how many are not visited is the trick here. Maybe this code is redundant, but I don't know. I need some time to prove it. This is if that's 0, if this is not visited. So not visited has to be equal to 2 of these, right? And like sum of not visited I'll do this, not visited plus plus, and the sum of not visited is so I, and then let's say that, okay, so failed has to be 1, so which one has failed is like, this is the sum of failed, this is fs will be equal to it.first here, and then you need to say if fs is equal to the sum. So you know that these two here can be differentiated, then this is and not visited equals to, then this is yes. Otherwise it's no. I think this, okay, so technically that's not correct, okay, whatever, let's just print in the map what happens. Okay, so there's like 2, 1, 2, 3, 4, there's 5, and 1 and 5 should be like the sum here, sum should be 1 and 5, so it should be 6. Sum should be 6, not visited should be 2, but yeah, so then this is the first thing here, map of a of 0 plus plus this we didn't add to. Okay, let's see this one, 1, 3, and 6. So there's like 2, then there's like 2, and then there's again 2. There's again, there's 3 here. What am I doing? 2 and 3. And then there's 1 here. So 1, 2, 3. So failed is 0, seems like. Failed is 0. And then there's one more case. This case probably 3, 7, 10. 3, 7, 7 is like 4, and here there's, okay, why is this null? This is supposed to work. This is supposed to be yes. Fail this one, of course. Sum has to be fs. Fs is wait, where did you get 6 from? Wait, the fs is fine, the sum is not fine. The sum of not visited is, this is visited. One is visited, 2 is visited. Yeah, this is the sum of 2 elements. Like the frequency is bigger, but one frequency is visited. One is visited and the other is this. Okay. Does it crash somewhere? Where does it crash though? Visited. If it's bigger than n, it's here. Which case does it crash? The third from the bottom. 1, 2, 3. Yes, this. Oh, this is long. Oh, I mean, long should be fine here. Okay, now see lost mixing potions. There are a total of n potions, type CI coins. Any kind of potions can be obtained in no more than one way by mixing several others. He has unlimited supply of k types of potions, but she doesn't know which one she wants to obtain next. To decide, asks you to find the minimum number of coins she needs to spend to obtain the type I next. The potions used in mixing process will be consumed. Moreover, no potion can be obtained from itself. So there's no cycles. That has unlimited supply of K types of potions. So there are some unlimited supplied. And then there are so did it pass? It passed. To decide asks you to find for each of the potions. She needs to spend to obtain a potion of type I next. Can be bought with CI coins. So each potion can be bought with CI coins. Any kind of potion can be obtained in no more than one way by mixing from several others. How do you... The total number of potion types and the number of potions... So number of potion types and the number of potion types Nastya has. So for each potion has some potions that need to be mixed. So cost of buying potion. So for each potion so unlimited supply. So some potions are unlimited. So I would guess something with like priority queue or something. And so there's N and K. N is the total number of potion types. This is like reversed, and that's why N and K, the total number of potion types is N, and then K is the number of potion types Nastya already has. Has this unlimited supply of. Okay. So, okay, so for each potion, then there are n lines of this. So, okay, so this is cost of all of these n potions. Is something like this. So cost of all of these n potions then the third line contains k distinct integers. So this k distinct potion with this ID has unlimited amount of this potion with this ID. So there is one of this here, the third potion. and the output is the minimum number of coins. So the third portion has a cost of 0. And then for each of like the other n portions, so now he says like, does it process will be consumed. Yeah, okay. Can there be a repetition of this? Distinct integers. So there's like some starts with an integer m, and then this is like cost, and then up to m, and then the new cost. Now what portion it is? It's like cost at this portion. But oh no, wait, so this has to be this cannot be done this way, because it has to be started from the smallest, the portion with the smallest cost. So I have to have like a vector of like edges, and then these are like n edges, and each of them has edges dot I resize m, and then each of these is like edges at I at j. This is the edge, and then the like I do a priority queue where this is what portion I'm currently looking at. And then inside the priority queue there will be like all these k portions that we start will be pushed inside priority queue. So no, I will go through all the n. This has to be pair, of course. So the cost can go up to 10 to the 9. Okay, so this has to be a pair as well. This has to be a pair as well. Then what we're gonna do is in the priority queue we're going to push the cost at I, and then with this associate with this portion, while PQ is not empty. If so auto, and then this is like cost, and this is index PQ dot pop, PQ dot pop. If cost at this index is smaller than my cost, I will continue, and then new cost, and then I will go over all of my edges v at edges at I. So these are all of the edges that like need to come into I, and then new cost will equal to cost at v. If new cost is smaller than cost at I, at my cost at I is new cost, and then oh no, we have to update all of the yeah, so no, not edges like this, but edges from the other side, right? Or I can do like the difference here. So what I could do is I could calculate all of the I will do this. I'll calculate all of these. So this okay, this is enough to be integer, right? So the cost of creating this potion is something like that, right? And then so wait, the smallest cost, think about this. How do you the smallest cost is the smallest cost, the cost will influence all of the edges that will influence exactly like so cost to create a potion. I will get myself a new cost, right? So this here gets myself a new cost. And all of them that actually like make the cost smaller, so I have to have like a reverse edge here, right? So I have to like reverse edges. These reverse edges will say, okay, this guy here affects me, right? But this guy here now, reverse edges at this guy here, like affects me, right? So this is what I'm saying. This guy here affects me, affects myself. And then okay, so when this guy is updated, I have to somehow update myself. So if the new cost is smaller than whatever my cost was previously, I will make my cost that, and I will go through all of the like reverse edges of, so everything that I contribute is like, so if the cost is everything that I contribute to, everything that I contribute, I get the cost down, right? That guy. So if it's smaller, I get the cost down to that guy. So this is how much down I get the cost. new cost here. This is how much I get down the cost, and then I push the cost at V and then V here. And this will be smaller than what I have in the priority queue, and this will just slip here. Cost at I. So let me just see if something I did wrong. Edges at ij minus minus, probably id minus minus as well here. Cost here going to be int max, probably. I mean, doesn't really matter because I read this here, right? And then I put this cost to 0. The affected edges oh, here reverse edges at ij pushback. Yeah, of course. Okay. Now here, what do we want? What do we have here? So two has a new cost here that should not get in. 5 and 10, so this is like a new cost. Let me just print the cost here. 5 and 10. Oops, let me just print the cost after this here. Uh, 5 and 10, and then this here new cost is 0. Why is 0 here? To 1, to what is 1 here? 0. This has 0 cost, 0 things relied on. So if this is 0 rely on, then well, so if edges at I dot size is, well, 0, it means that it cannot be obtained, right? Can only be bought. So this could fairly I could just continue here. Okay, this seems correct. Okay, this seems correct. Let me just see if there are some overflows. This should not be any overflow here because that should be smaller in return. So okay, so that should. Okay, now problem F looks like, so problem E got accepted. Problem F. Lisa was kidnapped by Martians. Because She watched a lot of TVs and she knows, okay, blah blah blah. Let's call integer Martian if it is a non-negative integer strictly less than 2 to the k. K is 12. The number's 51. Yeah, so it's non-negative and strictly less than 2 to the k. If k is 12, the number's 51. 52 to the... Yeah, okay, so these are Martians and then these are not. The aliens will give n integers. They will ask her to name any Martian number x. After that, Lisa will select a pair AI, AJ that are different in the given sequence and count the XOR between, so that number XORed with AI, okay, whatever. This is sure that the higher the calculated value, the higher her chances of returning home. Help the girl choose IJX such that it maximizes the value. So, so this IJX, so x has to be Martian number, which is less than 2 to the k. These integers are not guaranteed to be less than 2 to the k. Oh, they are guaranteed. Okay. They are guaranteed that they have to be less than 2 to the k. So, okay. So essentially pick IJX that for this holds. Okay. So you want to maximize this value. Maximizing this value, you want to pick x if like so the AND operation will make the bits very low. So the highest bit in both of these examples have to be very high, right? So to maximize this, you want like to somehow take a look at these elements and say that so x can be like arbitrary number, even 0 could be x. So essentially we want to take a look at the numbers with like the highest, divide the numbers by bits, and in each bit we kind of want to choose two numbers that are either with has that bit on or that has that bit off. The highest bit is either on or off, and then after choosing okay, so what if we do like a DFS, and then start from the highest bit, choose 1 or 0, then these numbers will be like smaller, right? Like we'll get to a smaller portion of the numbers, and then you do this again, and then but there's 2 to the k there's 2 to the k different things in the try. So like, I mean, so okay, so let's make a binary try, and then so we can either choose 0 and go to all these numbers, or choose 1 and go to all these numbers. In either way, we want to choose such that it would maximize, and at the end, like, what is the if there are two equal numbers, then I can make them the highest number. So yeah, okay, so let's build a try. Let's build a try. So I'll create this try here. And insert all these numbers inside the try. And then if x is so the insert function is just like if, so the direction is x and 1 over that bit. This is try here, these 2 pointers. If c of this direction is null pointer, then c at this direction, so c at this direction is another try, then so another node essentially, and then c at d insert x and then bit -1, so we get the bit down. And then if bit is essentially so bit comes to -1, then we just return. Okay, and now I'm just going to count like the frequency here. Also, we want to delete this try, and deleting this try will require a constructor delete c0 if, so this is like saying if c is 0, c is not null pointer, delete c1. This is essentially saying this, and then the frequency, and then here when we return, we kind of want to like get the frequency plus plus because we have reached this point, and then return that. And now this is like the try, we have all the numbers inside the try, and then we need to say that AI and IAJ. So okay, let's see. What is this? Okay, doesn't matter. So so if I go left, if I go left, let me just go left and right, 1 and 0, and then this is like the try, and then here let's say this only 0, and then 0 and 1, and like so forth, right? So this is like the try, and this has frequency, let's say this is 1, this is 1, this is 1, and then this is 1, let's say there. And now you want to essentially find the lowest node so that I can go through that lowest node and then branch off, right? This is what we want to find, because when branching off, this will be the highest bit in which the two numbers will kind of differ, right? So we want to find the lowest node in which this differs. So I could do a DFS, and then I could, like, when I come to this, when I merge two nodes, I will ask what is my lowest node that differs here, what is my lowest node that differs here. And we need to know which I corresponds to this guy here. So we kind of need to have a vector here. And just remember frequency pushback I. Here also this has to be I, right? So we know that this here corresponds to I, then this is the node. But after we have pulled that this is the lowest, so let's say that this is the lowest node, then like you want to go into the same direction here somehow, because okay, we find what is the lowest node, but after that we want to go into the same direction, because here this one, if this is here 1, then like I cannot flip them. So let's just see the standings. Can I see the standings? Okay, let me think about this. This bit here, this bit is, I will set it up to K or something like this, because so K will never be like, if it's 2 to the 1, then 2 will never be inside, so like k minus 1 maybe, I don't know, I'm not sure. But kinda supposed to be like this. Even I think even k is not that it's not different. But so x we can flip the bits here however we want. What we want in this try is so we want the longest common prefix, and in the subtree with the longest common prefix. Or if there are multiple longest common prefixes, we want to wait. So can there be a multiple longest common prefixes? Yeah, there can be. Of course they can be, but like I thought there's the What about for each AI? Look into the try and see and find the closest thing that would match this AI. So like for each, query the try into matching this AI, and this will give me like this will give me an integer. This is supposed to give me like a pair, and this pair is essentially what are like J and X here, right? And then we say if so there's like the best answer, and then int I, J, and X. Then if A of I XOR X and A of J XOR X is bigger than the answer, the answer is this: I is I, J is J, and X is X. And then we just want to print out do you need to print it in some of course, and this cannot be equal, so I mean yeah, of course. Of course that this cannot be equal to there are enough megabytes to this. So okay, so this, so there's like, so supposed to have a function remove. And then like if bit is -1, then count is 0. Then here there's supposed to be like a function merge. This function says if C0 is not null pointer, count plus C0 count. If C1 is not null pointer, count plus C1 count. And then here, when we insert, of course, we want to merge here. This count is, of course, frequency.size. So this will just kind of just update this path up there, right? And it will like merge them. Here, then when we remove it, we want, so when I remove something here, the direction in which I go is this. I go cd remove and then I do x and then bit -1, and then I do merge again. But the remove, I just count minus at the end when there's like bit 0, and then I return. Or when I like restore, count plus and then I do this. So these are just like fictional functions that I will use in order to avoid this case here that I and j cannot be equal. So this is just saying that try is like remove AI with the k bit, and then here I will restore AI with the k bit, starting from the k bit. Okay, so this is like kind of saying just avoiding some conflicts. And now we want, of course, to query, and to query is a bit different. This is where the magic comes into play. So if kind of bit is -1, it means that we reached we reached them. We reached the end, and then the end is essentially saying that if we reach the end, is essentially saying that, okay, there could be more frequencies here at the end, so we want to find the frequency which is not equal to, I mean, we want to find the integer we go over all of my frequency. If frequency doesn't match the integer, then this should return the So this is A, and then there should be X as well here. This should return F and X. So this is like some J's here. For each J in the frequency, if J is not equal to I, then I'm just going to return, and this can be proven that it's very fast. Okay, so what if, so the direction we get is the same thing, but now we have to question things. If C of 0 is null pointer, or C in this direction count is 0, so there's nothing there. So if it's not null pointer, but there's nothing there, we can't go there due to the removal of something, then we have to go to the other direction. So if this is not the same direction, then we have to go to the other direction. So we have to go query this, then query, then this is still the same. Otherwise, we go into this direction. This is the same, this is the same, but X should be transferred with the bit if and only if the direction is 0. If the direction is 0, then we have to flip this bit. Otherwise, we just like don't flip it. Okay, now let me just comment this out. Insert. Okay, what's the insert function? Pushback, frequency return. If it's null pointer, then we create a new try. Delete these tries. Okay, so this is C0, then you don't have to delete this because this is stacked. Okay, so something's NK and I here is inserted. So it goes like that, 2 minus 1, then 2 minus 1, then this is fine. Then it goes 0, 0. Okay, so then this is fine. But then as soon as this comes, no, insert. Of course, this is just let's add some brackets for more. Let me see here as well. I always forget that. Oops. Okay, now this works. Insertion works. Let's see if this works. This doesn't work. Let's see, remove and restore. This works. Query, does it work? No. Okay, query doesn't work. Query doesn't work. Let's here, let's assert false, just so we know that doesn't here. Doesn't come to this point. Okay, so this here is fine. If this is a null pointer or the count is 0, then I go to the other direction, and now the other assert that the other direction is not null pointer as well, because so this is asserted. Well, then we go bit -1, x remains the same, I remains the same, and a remains the same. Oh, here it has to be a, not x. Here has to be a, and here of course this has to be, oh, this is D, so this is in this direction, and then okay, this works. Let's just say this 1 3 28 to this number. I mean, I will just submit it, but I'm not sure if does it have to be the smallest x? No. So I will just submit it like this and see if it fails on the first test, we don't get any penalty. Fails on the first test, but why? Why does it fail on the first test? 2 to the 4 is 16, but x is like way above that. So can we just do like -1 on anything here, on everything, on every? So wait, k minus. Okay, so 12, it says 12. Is it correct? Here it says 0 0 -1. That's not correct. That's not correct. This is the third case, so this is here. There could be 0. One of the things can be 0 as well, so that's what probably bothers him here. This is guaranteed that it will exist. But why 0, 0, minus 1? Oh, the answer, of course, the answer is like, okay. That kind of makes sense. But here, 14 and 12, does it? 14 means that it's 2. Yeah, so that's like 1 and 2, 1 and 3 is chosen, which means that, yeah, that's different in 2, that doesn't matter. That should be fine. Okay, wrong answer on test 2. Okay, let me see if someone solved that. No. Wrong answer on test 2. Okay, so what's wrong here? Is it possible like that the integers are really like big here? Let me try something which is like smaller than 2 to the 30. So 2 to the 30 is like this integer. Let me try putting this integer with some other okay, let's try like 2 integers of this size. Okay, this asserts failed. Oh, wait, do you have like some assert that fails here? No. But yeah, so two integers like this, and it says 1 and 2, and then you get the wait, what? Huh? Yeah, of course it has to be smaller than that. So yeah, of course it has to be smaller than this. This has to be 0. If both of these are, if the direction is 0, then if the direction is 0, then I'm doing this. Wait, what is x here? Oh, x is 0 because I don't want to do this. I don't want to do anything. Yeah, that's correct. That's correct. I have to print x, right? I have to print x. Okay, let's see here. Then one of this integer is smaller than that guy by 1, so that means like 1 you can't do anything. Let's 1 more, then you no, 1 more, then you have to do something with x. From this side. Yeah. So now x is like smaller because I have both of these here. Well, that seems correct. That seems correct. First, I understand that seems correct. For example, K12 Martian, so just 2 integers. total 30 is fine. This is fine. This kind of works. Let's say that this is 0. Yeah, so that is supposed to work because and that's correct. This is 1 and this is 0. Let's put one more 0 here and let's put like now this is correct. You see, this creates this is the maximum value. You can choose these. And this is as the XOR. Let's put both of these as 1, then this value is chosen differently. I don't quite see what's the problem here. So let's see if there's some bug here. For every frequency that is not equal, we immediately return this and x. So let's see the query again. So this is the query is AI, then I, then k minus 1 is the bit, and then the x is 0 at beginning. That is correct. Then you see if A has that bit on. If that's bit on and that's null pointer or the count is 0, then we don't go. We look at the other side. We want to go where this bit is the same. But no, actually this is wrong, right? Having the same bit as this guy, it's not quite correct. I see why it's not quite correct. It's not quite the logic we want. I'm disappointed. Because there could be a contra example where you go first like you kinda go on the path where you are led to on the same bit, the equal bit you have. But then quickly do this. But what you can do is, yeah, of course, yeah, no, this is correct. This is correct. This has to be correct. If it's not the same bit, if the bit is different, then this, it has to be the same bit. This has to be the same bit. But if the bit is in the direction to travel 0, then we want to make this direction then 1. This is correct. If it's not the same bit, then going to the different bit always loses, because X will be like always something else. And then you can't just, so that this is correct. This is correct. Merging here will always work okay. And then removing here, this removes the count, but then like merges this. And restoring this restores the count and then merges upon the you have, so you iterate through all of them. The answer is this: I, J, and X. Then we restore that. This is supposed to work, and then we delete the try. I'm not sure why this doesn't work. Vlad at the mountains, I will. No, I don't know if this is supposed to be easy. If this like problem supposed to be easy. I'm not sure. I don't know. I-J-A-I-A-J. The count is just taken from the children. I don't see how this could anyway. Yeah, so that's not null pointer definitely, and then that should be yeah. I mean, I don't see any mistake here. I'm not sure. About G, I don't quite. I mean, is it possible to construct some rules starting? Oh, so there are queries. Okay, so G seems like. Seems backwards. Wait, from mountain ing, if the energy will be restored. As a height of hi. So he can move upwards and he can move downwards, and then the height of the mountains. Well, isn't that like so if there's a road between, okay. So the total energy spent between some two cities have to be, so the total difference have to be at most this E number here in negative. Because it's still like commutative property, you have this commutative property. And then the other constraint is, okay, it has to be connected, and then the other constraint is that what is the minimum, what is the maximum spent on this path, probably. But this is a graph, right? This is a graph, so it's a very interesting problem. Very interesting problem. The spending of the energy probably there's something like with DFS trees here. with some, like, if I root them in, if I root it somewhere there, and then you kind of but I'm not sure. I'm not sure about this. I'll have time to think about this. I wanna maybe just fix my submission here. I wanna fix my submission on F. So if there's some other number that is equal to this, we go there, we go there. We just don't want to go to the other side. That's our priority. So this is in the statement, you cannot pick two the same numbers, two same things, right? Is there a constraint on X other than that? That should be like, wait, can it be negative? So like, no, right? N is never 1, so that's good. There will be always I'm not sure what. Wait. No, they're all inside the range. Two and three. I have absolutely no clue what's wrong. This goes into the same direction. Right, maximum. There is another problem which is similar to this, maximum XOR subarray. So I code this the same way. If this is, yeah, this here is like we want the other thing here. This is, if this is a null pointer, if we can't go into this direction, or this direction is empty, which means that this will be the case for most stuff. Null pointer will never be the problem. Then the other direction should be possible. And then the other direction, we query the other direction by the by a bit smaller and then the same x, because x doesn't quite matter. This would be anyways like 0. So we XOR the x's, and then x's kind of say, wait, if it's in this direction, then we XOR the x's, and then let me just print out the answer. Yeah, that makes sense. It's 1 minus. It's 2 to the 30 minus 1. This is the best you can do. I don't know, like, I mean, this works. What else would it not work? Like, what about this here? What about this? That's correct as well. I mean, I don't frankly know what. Is there some constraints here that we're missing? IJK, the value should be maximum possible. What about 0, 0? $15, because it can't go any further than that. I don't know. I frankly don't know. But I will go over all the tasks because still I need to explain them. I'm not sure where I went wrong on this task, but I possibly could solve them all. But got stuck on A because didn't read the tasks properly. Did it take me 16 minutes to solve A? This is insane. What can I say? What can I say? Okay. Hope you saw that sometimes it's not your day and you just I mean, I don't know where did I went wrong. Let me see what's his solution. He uses try as well. I don't know where I went wrong. I don't know if it stays, if it says, but whatever, doesn't really matter. CodeForces. Can I go into the view? Okay, so let's explain the problem. So A is like a really stupid problem because first, like, I thought that each, so here it says there are a total of m steps, right, on the escalator. So if you can imagine that like all of these m steps are like this, what I actually saw, because here and it says and ith step has a height of I times k. I saw that the ith step here, if this is the first step, has a height of 1 times k, and then the second step I saw that the height from here to here is like, this is the second step, and then from here to here is like 2 times k, and not from here to here. So in my mind the steps were like this. I don't know why there won't be like this, but I just thought that something like some trick, because like when you say that the I step has a height, you mean that the height of the I step, you don't mean that the height where the I step it actually belongs to, from starting from here, is 2 times k. It's just confusing. Like you could have said the I step has a height of k, and then you already know that you already are very better. But okay, and then it says like two people with different heights a and b, or some heights a and b, stand on different steps, and the height difference between them is equal to the height difference between the steps. And this is when the two people can have a conversation. But what I did not see is this like equal. I saw like at most or something like this. But you need to kind of bolt out this, because this is quite an important thing. And then it's just much more like complicated here by this example here, and because there are so many parameters, it makes it hard to wrap your head around. But okay, at the end, what you needed to do is just get this absolute difference between them. And if this difference is 0, there's this case that, like, if the difference is 0, then the people actually have to be on different steps, and this is kind of as well, like, important to notice now. And you need to check out that the difference is divisible by k, and then the k times m minus 1, because one step you're already in and the other step is like he's like at the end, so it's m minus 1, actually it's not m, and this is bigger or equal to the difference. So there is enough of these steps between your yourself and this other guy, or whatever, the Vlad and this other guy. And then you do this for each of the different guys. So for each of the heights, then you check this out, and the answer is added upon the answer if this is true. Okay, so that was problem A. Problem B, parity sort. You could only swap elements if they are both even and both odd. So let me just, I don't know, again, something happened to the camera. Okay, so like OBS is quite slow something until it connects to the camera or something. I'm not sure, but okay, whatever. So you could swap only two elements if they're both even or both odd. So the thing is that if this is the constraint, you can look at this as like you can sort only the even separately and only the odd separately in places where they belong, where the even and odd belong. So if you have something like, so 7, 10, 1, 3, and 2, so this is odd, this is odd, and this is odd, and these two are even. So you can only swap you can only sort the even numbers in the places that they're even, and then the odd numbers in places that they're odd. The places that are initially are odd, because the place here cannot change from even to odd, because you can never quite swap an even and an odd number. So this can never change. And this was then the conclusion, that you wanted to have this even and odd. I didn't even use this index here for the even and odd, but I kind of remembered where are the even indices and where are the odd indices. These are just these places here. Where are they? And each of these places, I will mark them from this is 0, 1, 2, and this here essentially is 0, 1. So this is the color 0, 1. So at index 0 on this, where that even number is, whether this odd number has been previously, you kind of have this. So this odd ID is, so if there are all these places, this is like at 0, and then at 2, and then at 3. This corresponds to 0, this corresponds to 1, this corresponds to 2. And you remember this odd, and then you remember this even. The even IDs will be where the even indices can reside are on 1 and 4. So this kind of here corresponds and this corresponds to this. Then you sort the even and the odd separately, and for each of the even numbers you need to put them back into an even place, but this even ID is what this place is going to be, and we put this number that is sorted now, and the odd ID, in this odd ID place we put this number here. And then we check if the array is sorted or not. If it's sorted, then it's yes or no, otherwise, because in no other way can we sort more than what we sorted here. Yeah, this was good problem. A I didn't like. B I liked, because it's very simple. It's very division tree like problem. C is well, there are some colors, and you need to construct a path where it is divided in like some blocks, and each block is like different colors here. But each block has to be like k units in length. And you can construct this by like one or more blocks of these like colors. And then the trick here is that each color here is denoted by some integer. And essentially you jump only to like to some place where to the right where it's like on the same integer as like you are. And to notice here it's fairly simple, that like you start from the place from the beginning and you end at the end place at the just a second. So you end at the last place. So these two places have to be included. And you don't need to jump to any other color, because you can always jump the whole length of the array. So it doesn't quite matter whether or not you jump to some other color. So in fact, that there are at most two colors that you're interested in. The place with the color of the first element and the color of the last element. So sometimes they can be equal, and this is a edge case, but we'll get to that. So here we say that the front is like what is the position of the the leftmost element. So the leftmost element where you reached that the colors. The front color, so this, like, let's say that this here are red color, right? So let's say that the front color is red here, this one. Then if k is 3, then you need at least 3 of these. You don't quite need this. So what is the leftmost position, such that there are at least 3 colors, exactly 3 colors of the color that matches the first element, and this is the most position. And you do this for the last element's color here, and this is the position where this reaches. And this position and this position have to be, so the front position have to be less than this position, because if somehow we went the return, so the color we need to go over here, and then we don't have enough colors on the front side to match with this. So if something like this would have to occur, so like 1 1 1 1, and let's say it's 4 4 4 and 4 like this, then so this is some other color, of course. Then if k is equal to 3, then you would kind of go to here. This is our front position, is going to be our front index, and you would go from here up to here, this will be our back index, and there's no way to reach from the front index through the back index like this, because you can't go to the left, you can only go to the right. And this is this check here. So if front is smaller than back, both of them have to be equal to k, so at least k colors have to be reachable from the front and the back. In case the colors are equal, then either on the one side can be a k or on the other side can be k, because what you can do is, if I would to end with 1 here, at the end, what I can do is, like, I can pick this one, and then this one, and then this will be 3Ks, and I don't quite care about that the back has 3Ks as well. It's like either the front or the back has 3Ks. In hindsight, like, it will be like if the front is k, or the back will also k, and vice versa. But this is the only condition that we need to check. We don't have to check the indices if the indices are to match like this. So okay, so this was C. Problem D. Problem D, you had given prefix permutation sums, and then so like you have given prefix sums of some kind of permutation, where one element of the permutation, one prefix sum is like taken away, and then you need to know if you can construct a permutation that matches this prefix sum or you cannot. So it's a little bit more complicated, but what you can see is just like casework. All of the prefixes, so the prefix sums, if there are 4 numbers in a or there are 5 numbers in a permutation, there are 4 differences between these numbers. And the first number denotes something that starts here. Denote some number. So like, let's say the permutation is 1, 2, 3, 4, 5. Then the prefix sums is 1, 3, 6, 10, and then 15, right? Yeah. So the difference between these two numbers is actually this guy here. So if you can see that here 1 we don't have any difference, but let's imagine that here's some 0. But then here this difference is 2, and this difference is 3, then this difference is 4, and this difference is 5 between these two numbers. But now let's imagine that we take away some number. Let's imagine that this number is taken away from the prefix sums. Now this difference between these two numbers, we don't know that this is actually like 3 and 4 here. We only see this as a 7, because 10 minus 3 is 7. And now what you can realize is that this difference can sometimes be bigger than n, which in the case that we have all of these numbers prefixes can never happen, because the most number will be like n. But here we see 7, then like this is bigger than 5, which means that 7 is made of 2 numbers, of some 2 numbers. And it's only a casework in which you need to prove that in fact a permutation can be created. And okay, so here we go through we create all of these differences between these 2 numbers, and I put them in a map. And then you have this visited is, you say, okay, if I see this difference of 2, then I know that a 2 is inside the permutation. But if I see it twice, some difference, so if I see some 2 and here, and again like 2 here, then it means that one of these 2's is made of 2 different numbers. Let's say that I have some prefix sums that look like 3, 3, that looks like this, 6, and then, yeah, so 3 and 6, let's say like this. Then I know that the first here, 3, is, let's say 3 here. And then the second 6 could be also made of 1 and 2. Because remember, at most one of these can be made from some other material here. And this is permutation. 1, 2, and 3 is a permutation. 3, 1, 2. So visiting means that I have visited 3 here, and if I have visited, if I have this frequency, if it's 1, I put visited. If it's more than 1, I put visited is true, but also failed. I actually remember that some number has made more occurrences, right? More times occurrence. And then yeah, so if it's failed more than 1 time, it means that it's no, it's definitely no. But because you cannot have more numbers removed, only 1 number will be removed, right? So yeah, so that's one thing. The other thing is which one are not visited, and the sum of them have to be equal to this like failed sum that so this failed sum has to, so this 6 here that so this essentially, this 6 is a prefix, but this would be turned into 3, and this will be turned into 3, because the difference between them, 6 minus 3 is 3, and this 3 minus 0 is 3 again, so that would be turned into 3. So 1, 3 is here, and 1, 3 is here. And this 3 is actually like saying, okay, can we make this 3, they have to be equal, and the not visited have to be 2 equal. Not also if it's failed 0, so there's sometimes there could be no fails, but not visited is 1. This is the way that like this was because you could remove the first element, I think, always from the think something like that. I'm not sure, but I needed that. Failed sometimes is 0 due to the I don't know when is 0. There was some case where this was 0. Okay, it doesn't matter. The other thing, okay, so so this is the last task we solved. There were some potions, and the potion of type I can be bought with CI coins, but also some potions each potion can have a recipe that can be created from other potions. And now Nastya has like unlimited supplies of some cake potions, which these can be bought essentially at 0 cost. Cost of them are 0, but then you have like to say for each of the potions what is the minimum number of coins she needs to spend to get the potion of type I next. So the potions with unlimited supply are actually cost of 0, these potions here, but potions that have some cost can actually make the cost of them a little bit lower if you are kind of carefully combining them. But first of all, you need to see that you need to combine potions from the least expensive to the most expensive ones. If you do other way around, it won't kind of work, and that's why I use priority queue here. The cost of all potions is right here, and then all these K potions are just set that the cost have 0, their cost is 0. And there are two vectors. There's this vector edges, and then there's vector reverse edges. Edges means that what potion can be created with what other potions. But reverse edges means that this potion influences this potion here. Because if something happens to the price of this potion, immediately affects the price of this potion. And thus, like when you have a priority queue, in the priority queue I will put all of the costs of the potions and the potion index. I will start from the least expensive potions. I will always see if the cost is smaller than C. So if I have reached somewhere cost smaller than C, then I will continue. That this here allows me to add in the priority queue more potions, but the old entries in the priority queue will never be processed, will be just thrown away. If there are no recipe, so if the edges, it means that this potion cannot be obtained by mixing. So this if the list is empty, then the potion type I can only be bought, so it cannot be obtained by mixing. It means that I cannot obtain this potion by some other potions, and thus I cannot influence some further potions. Okay, what if I can obtain this potion? Then the new cost of the potion will be the sum of the costs where this potion can be created. So these are edges, so these some edges so this is how I create this potion. So this is the recipe, right, of the potion I. Then I get a new cost. What if this cost is smaller than my existing cost? Then something will change, and exactly things will change. That my cost will change to the new cost because I can access now. I can create this. But also using the reverse edges, I can go and I can eliminate from the cost of the other potions that myself are included in their recipe, and then the cost will be eliminated by the difference in my cost. And this new cost will be added into the priority queue. And because this new cost V here will always be smaller than a cost which exists inside the priority queue, this cost, the old cost, when it comes, it will trigger this if statement and thus will not be processed. So this priority queue will only run in 2 times n or something like this, so O of n. And then there's log n, the processing in the priority queue, thus making it n log n out. This can be easily proven with some contradiction, why you don't want to start from the most expensive potions, because these can be made, the prices of if I start from the most expensive potion, then the most expensive potion will never affect potions which are less expensive than himself, because the price will be included in that. So in this way we start from the least expensive and go to the most expensive potions and process them in order. Problem F was using, problem F, I don't know why my solution doesn't work, but I will just let me just submit problem F one more time, just in practice mode, just to see if I can maybe debug it. But problem F was essentially trying to maximize this. Let me just do this. Okay, now it gets accepted. Excuse me. What did I change? Wait, what did I change? Let me compare it. Can I compare it? Compare. Okay. I have no clue what I changed. Did I change something? Compare previous solution. Whoa, I added only brackets here, and this was it. So this here is like saying that the priority here has this this AND has lower priority than this. So this was executed first, then ending this, and that gets accepted immediately. I'm blown away. But so F. So you have to maximize this equation, but you had to choose different A and J values, so different elements AI and AJ. How you do this is by creating a trie, and this trie is essentially a tree, and as I explained in the problem while I was solving it, this is essentially a tree, and then this tree is like you start from the most significant bit, so this is the most significant bit. This here, this node divides the most significant bit, either it's 0 or 1. So if you read this number here, it's 0, 0, 0. If you read this number here, 0, 1, 0. So 0, 0, 0, 0, 1, 0, 1, 0, 0, and then there's like 1, 0, there's 1, 0, 1. So all of these numbers, while this is the most significant bit and this is the least significant bit. And then what you do is like you put them, all these numbers in this trie, in this binary trie. And for each number, again, you want to remove only this number from the trie when you're processing them. And what I do is I fictionally like remove this number from a count variable. I won't go into detail how I do this. Maybe in the next video I will, in some other video, probably not the next video, but some other video I will go over like creating a binary trie. But my approach is just like I code it like this from scratch. I don't use, although you could use some other techniques, but I do this with recursion because it's, for me, it's more intuitive how it works. So I remove it here, I remove this count, and then I restore it back when I am done processing this value. But what in the query of the tree, so like the trie has an insert function always, and some like possibly some query function. And this query function essentially goes through the trie, but it goes only in one path, and this one path is at most 30 bits long, 30 recursion depth long. This is due to the bit size of the number, so it cannot go more than that, and thus limiting this complexity to an n-log n factor, right? N-log this maximum of AI, which is around 30, right? 30 n log k or something, n times k, but k can go up to 30. This is what I want to say. So I go over this query function, and this query function essentially goes and it says, okay, if I'm processing, like let's say that this is my trie, right? And let's say that I'm processing this number here, 100. So essentially what I'm saying is I will delete this 100 from the trie. So I will kind of do this. I will go to the try and I will delete here. I will say that there's 0 count of this guy. And now in this tree here, there will be 1 count, there will be 1 count, this will be 1, this will be 1. And then here, there will be merged of 2 count, and then there will be 3. And exactly 3 numbers are in the tree here. 1 and this here, 3 numbers. So now when I query out, so my operation now of querying is of this number here, 0, 0, 2, so this number here, and then some other things. But this is the operation. And we say, okay, we have this number, right? We want to find some number that matches very closely to this. Because the XOR, remember that the equation is like this, and thus making it so this X here means that whatever I supply in some bit here in this number, the other number will also change here. So if X is 1 in some bit, then this number will change and this number will change. I mean, this here whole thing will change. Okay, so essentially here when you're in the first and you're processing this number 100, you want to say, okay, do I have a number? I'm looking at this most significant bit right now because I'm right here. And then do I have a number which has this bit 1, the same as this number? Yes, I have a number. Okay, then I go here because the count is 1. So I know that one number exists such that like this. Then I look at this bit here. Do I have a number that has 0 in this bit? And I see here, because here I have some other edge which has a count of 0, this null pointer edge. And I say, okay, there is this number, this edge is 1, this edge is 0. There is some number with 0, and I go here. And now I am here in this. And then I say, okay, is there some number that has 0 in this place? No, because here the count is 0. So I have to switch. I have to switch to this place. And I have arrived here at the end where I say, okay, this is it. I have reached this number. And what is this number? Okay, this is this number here. And I matched them. So for this number, the best number to found is this guy. And I check if this is better than what I have in the answer. Maybe it's better, maybe it's not. Maybe there's some other match better. So that's why you have to update the answer here. And essentially this is it. If this equation is better than the answer, we update the answer, and then we update these like values which we matched ij and x. This is like what I've matched, what is the best match till now. If you want to know more about tries, probably Googling them or researching that on that topic is interesting. I won't comment anything on G since I did not solve it during the contest, but I'm sure that it's a easy. It's an interesting problem since it probably requires some kind of data structure, but I'm not sure. So yeah, so thank you guys so much for watching, and I see you in the next CodeForces or EdColor round.